All right, welcome everyone to the Tools and Technology Seminar Series. There's a sign-in sheet that I just sent around going this way, so if you haven't signed it yet, please do so. As you know, it helps with the pizza, so that is greatly appreciated. Also, I have begun scheduling people for next semester, so if anyone's interested in presenting next semester, please let me know, or if you've got suggestions of people, I'm happy to contact whoever. I'm always looking for volunteers. Today I'm pleased to present our speaker, Alberto Figueroa, who is Associate Professor of Biomedical Engineering and Surgery and is going to talk to us about Crimson.
Thank you, Marcy, and thank you, everyone. It's really kind of a pleasure to be here. So today I'm going to tell you about a set of software tools that we develop in the lab for blood flow modeling. I'll try to talk a little bit about kind of maybe foundation behind some of these tools, but I'll try to make it mostly practical. And if you have any sort of questions along the way, please, of course, stop me. So first, I'll tell you a little bit about the different components of the software, and I'll do three technology demonstrations. One is a simple graphic-based boundary condition editor, then some work that we're doing on automatic control of flow, and then some data simulation techniques based on Kalman filter. And then I'll show you a specific example of surgical planning that we've done in the hospital. So what we do, I think maybe for you, you don't need this kind of explanation, but we do data-driven computations, and our computations are blood flow simulations. So we get information from the clinic that can be anatomical, it can be flow, it can be pressure, it can be perfusion, it can be wall motion, basically anything that can be used to make your model more relevant and more accurate. We can use it. So this is an example of the biggest simulation we've done. This is physics-based. This is Newton's law that we're solving here. It's a full-body CT scan, about 100 vessels or so. And this entails solving fluid structure interaction simulations. We solve not just the equations of fluid, but interaction with the wall. And you can see this thing pulsating. This is 10 representative locations for the pressure field. This is the overall pressure field. And this is the same thing for velocity and flow waveforms. And obviously, you look at the brain, the circle of Willis, you do have the level of detail there. And the idea is once you have these, and this is properly calibrated, it's physics-based, so you can probe for anything that you think might be relevant from a mechanobiology perspective. So here, for example, we are post-processing the shape of the velocity profile in the infrarenal aorta. We know that that's a location that is very prone for aneurysm development. We understand why. So this is the kind of things that modeling can give you. And what we explain to clinicians, which sometimes I have a hard time obviously understanding what's computer graphics and what's physics-based simulation, is that we don't really start doing anything until we have a match of the clinical data that is given to us. And this is what this image here shows. The plots here to the left and to the right are our waveforms, and on the edges of the pages we have actual clinical data. We basically, there's a lot of parameter estimation and adjusting operation until we get a good match. And from there on, we say, okay, now we can start. So the key applications of the field is we use it a lot. We actually have a very active hypertension research in my lab. You can use it as a microscope, for instance, right, to try to get some insight into whatever it is that you're studying. The FDA has mandated almost 10 years ago or so through something they call the Critical Path Initiative to use new technologies for accelerating the development of cycling, production cycle of drugs and devices. So a lot of computations are done to optimize devices nowadays. There are already examples of software solutions that are used to make clinical diagnosis. This is actually the company of my previous advisor. When I was in grad school, we started developing these tools. He abandoned his tenured Stanford position and started this company, which almost 2 years ago received FDA approval for diagnosis of coronary disease. The idea is to use fluid-based simulation in this case to predict the severity of a stenosis. And then what always caught my attention and a lot of people in the field attention is the idea that maybe one day you can use this type of tools to help surgeons or interventional cardiologists to come up with the best procedure ahead of time, right? There's a lot of guessing in the work, so the idea of surgical planning. And the example I'll show you at the very end is one of such examples. So first, a little bit of history about the lineage. You know about software, so you know that you basically cannot reinvent the wheel. Even a relatively straightforward component like the massively parallel stabilized finite element fluid solver, that takes pretty much a career to develop. So you can't really start by doing it yourself. So of course, what that means is that we rely on our advisors' work and our advisors' advisors to kind of put together over generations a series of products. So this part here is just a kind of core finite element solver for the fluids equations. Okay, it really started off even before RPI, Rensselaer Polytechnic. We continued to develop a Stanford big push, and now this Crimson software stands for cardiovascular integrated modeling and simulation. We continue to develop. I should say that this is I was in the UK before I came to Michigan, so I've been in Michigan for just over 2 years. So this is funded by a European project, ERC, and our plan is to make it open source at the end of the project. So one of the goals that we have is to we think that we have a good starting point, and we want to integrate best-in-class open source components for this. So some of the things that we have now in Crimson that Symbascular didn't have. So we have a completely new GUI. I mean, you could go to Symbascular and see the differences, but this is based on a medical image visualization and medical image processing solution called MITK. So this is developed by the German Cancer Research Center or Foundation. So open source, of course, is based on industry standards for ITK, VTK. Very versatile, and the idea is that this is a project that is supported by a team of 100 people. So whenever they come up with a new release, we have to do relatively minor tweaks to our software to then plug it into the newer version. Something that we find extremely useful is that it has a Python base, kind of like ParaView actually. So we can do lots of things in modeling with that interface. In what we do, as you probably know about this as well, but there's two ways of dealing with geometry. The most common is by far a discrete approximation for the geometry, like a discrete solid model, an STL or something like that. We are working on that, but we always have an analytical description of the geometry. We like that. For historical reasons, we started that way, but basically we have a NURBS-based approximation. Once we have a segmentation, we do kind of an analytical interpolation. And that there's a number of advantages there. It makes surgical planning very easy because you can do parametric alterations of your geometry very easily. Boolean operations are simpler, of course, if you have CAD model rather than doing them with mesh. Yeah. So we have these things already incorporated. We also incorporated this library for data simulation that is based on a family of methods based on the Kalman filter. This was done by another, in this case, a French institution. It's called INRIA. It's kind of a set of national labs. They're, very mathematically oriented. So this was quite a bit of work, actually. And I'll show you an example of how these parameter estimator libraries work with our code. And then, one of the things that we want is to have this as an easier to use research tool. Maybe saying that it will be used in the clinic is too naive because it's still too, requires a lot of expertise. But we certainly want to make certain tasks simpler. And I'll show you in a few slides. One of the, most mundane operations for us is the issue of boundary conditions in our computations. And we just came up with a way of pretty much drawing the boundary conditions, not having to rely on manipulation of ODEs that is very error prone and very cumbersome. So I'll show you that. From a research perspective, we are really interested in transitional physiology. So what happens when you start running? What happens when you have a big cut? What happens when you go into the OR and you have anesthesia and then it changes your conditions? So the body has a series of mechanisms that control adaptations to changes in pressure and flow. We're incorporating that. And all of these prototyping, basically the design of the boundary conditions, the fact that you have a series of controllers that exchange information between different parts. The thing is, you can do it very easily at a higher level with this Python operation, and you basically almost never have to change the core fluids code because these are things that happen on the boundary. You can do in a simple way. So that's the reason we are designing it. And then obviously we have additional features we're not going to explain today. So this is kind of the thing about the family of methods and tools that we have. So let me just demonstrate the Agile boundary condition editor. But the one thing about blood flow modeling, so this is a theory slide, if you want, is it's kind of explained in this picture here. So when you do image-based modeling, obviously you rely on having some image data for the patient. Inevitably, it's gonna stop at some point, or even if it was like full body, like the one I showed you, at some point you're not gonna see the vessels. So what you need to do is whenever your three-dimensional model, which is this kind of red cartoon here, ends, you are artificially truncating the vasculature there. Obviously, the vasculature continues, you just don't see it. So you need to come up with, if you thought about this problem from a traditional fluid mechanics perspective, you're like a fluid mechanician from the 1960s, you say, okay, I'm solving for velocity and pressure, where's my flow and pressure boundary condition information? Well, forget it. There's no way that if you have a vessel, a tree with like even only 10 branches, you're going to have 10 measurements in the clinic. So instead, what you need to do is you need to come up with simpler models of the circulation that you couple to each of those outflows. And you basically have what in mathematics is called a variational multi-scale method or a multi-domain method, where you have a part of the overall computational domain in which you have a modeling approximation, in this case, 3D Navier-Stokes, and then these peripheral parts that have a simpler model of the circulation. The simpler model ever is a resistor. It relates a change in pressure with a flow, or in circuit theory is a change in voltage with current. You can make more complex models with maybe you add some capacitors, you have some diodes, etc. Or you can have linear propagation theory or an impedance function, or etc. The idea is that it's a simpler model, but nonetheless, it's something that you can couple at this interface between the three-dimensional end of the three-dimensional domain and the boundaries. So this is the kind of approximation that we're making. For example, one of the better known reduced order models is this thing called a Wien-Kessel, okay, which is a series of a resistor, a compliance chamber, and another resistor. And if you parameterize this wisely, you can basically approximate the behavior as far as overall flow and pressure distribution, any vascular bed that you want, basically up to some approximation, of course. So let me show you at this point, I'll show you the actual interface. So for those of you who are familiar maybe with Paraview, you'll recognize kind of the overall layout. So we have a menu here. We have, this is the image data of a particular patient that we did. So the 3-view. So this is, in this case, we're looking at a problem in which we are concerned both with the aorta, as well as, this is the aorta, the red vessel, as well as the pulmonary vessels. So this is live, and of course I'm not the one who uses the software on a daily basis, so I hope I don't mess up. But I'll show you how this boundary condition editor, the idea is that at every single outflow branch, you need to come up with a model, right? So so this is something that you have to be here, and then you have to be here, and you have to be here, and here, here. Okay, so you basically get to choose from a series of boundary condition types. You can still apply a velocity boundary condition. You can be dealing with a boundary wall that you model as a compliant vessel, so that would be that. You could apply zero pressure, a Wien-Kessel, no slip, an initial pressure. But the cool thing here is this kind of graphical interface towards boundary condition specification. So we're going to apply a boundary condition in one particular phase. So we're going to select the phase. Let me hide there's multiple things here that I'm showing. Let me just choose this. And then I launch the editor. So here you're going to have a whiteboard where you have the main components that allow you to draw any circuit that you want. Okay, so for instance, this guy here, this is going to be the interface with your three-dimensional outlet. And then let's say, okay, I'm gonna, if I wanted to draw a Wien-Kessel, I would just choose my resistor. I would choose my capacitor here. And you put it there. Then I choose another resistor. You could choose a prescribed ground level here and here, and then you save this, and this, going back to the presentation now, and of course all the things that we have here. Let me just show these. We can take care of basically all the modeling tasks, including mesh generation. So this is the final element mesh. And all the boundary condition specification is actually done on the analytical model, not on the mesh. Because when we go through the modeling process, we do a lot of mesh refinement. And fundamentally, the boundary conditions belong to a model, to a conceptual phase, and not to a specific mesh. So this is another practical reason why having an analytical model is a good idea. So, obviously I could be talking about this for a long time, but it kind of gives you hopefully an idea of what this GUI looks like. So I demonstrated this part now. So yeah, I mean, the powerful thing about this is you can basically design any circuit, and the code will assemble. At the end of the day, that lamp parameter model results into an ordinary differential equation that relates pressure and flow. And then that equation is assembled in the background and is coupled implicitly with three-dimensional Navier-Stokes with a Dirichlet to Neumann kind of operation, okay, where you're basically exchanging information between what you get in the 3D part with the 0D part back and forth until you have the same solution at that interface. So this is kind of the details of the operators that, regardless of the design of the circuit, they're being assembled in the background. So this, okay, makes the drawing easy, and it also makes it very easy to enable communication between different parts of your reduced order models. So in this case, this is of course an idealized aorta. And what we did here is we have, for every single vessel here, we have a standard, not for every single, for the bottom four, we have the standard Wien Kessel. So you see a resistor, a capacitor, and a resistor. And then we have two additional phases here. This guy here, we can design a circuit that behaves as a heart model, okay? And in this case, you see this is a diode, so that's going to be the mitral valve. This is another diode, that's going to be the aortic valve. This guy here is going to be a time-varying voltage generator, meaning a pressure generator. And again, the reason we do these things is because, A, we parameterize information that we may not have, and then we actually have a model rather than a direct measurement, okay, for these things. And then this guy here is an idealization of a coronary vessel. The coronaries are the vessels that feed the heart muscle, the myocardial muscle itself. So these are a different circuit because these guys, as they are embedded in the muscle itself, they feel an amount of extra external pressure because the myocardium, when it's contracting in systole, is squeezing the vessels like crazy. So they are the only vessel in the body in which most of the flow doesn't happen in systole, but in diastole. So when the muscle relaxes, gives them a break, and then flow actually goes to the other. So if you're doing something like this, obviously you need to have a way in which the pressure of your heart model talks to these intramyocardial pressure components that are part of the coronary models. These two things, because we're using reduced order models, they are not physically in the same place, but in reality, they are talking to each other. So you need to be able to have the ability of broadcasting information. And this is something that these graphical design of boundary conditions and Python control allows you to do. So I'm just going to skip this. But you basically have, when you choose one given resistor, you can make it dummy. You can make it, okay, I'm not going to do any sort of transitional simulations. It's going to have a fixed value. Or you can say, okay, I'm going to write my own script that simulates a certain behavior that you know is happening physiologically. So this is very easy to do. And because we have Python, I mean, we have functionalities in terms of mathematical symbolic math that are actually not from MATLAB. I mean, we have these NumPy and SciPy. You know, you get a lot of functionality in there, which is great. Okay. So I'm just gonna. This is more on the physiology side. So since this is mostly about software, I'm gonna skip it for now because I want to show you the applications. And if I have time, I'll come back to this. But this is a specific example that shows how we utilize these control and this communication between different parts of the vasculature when we're trying to simulate adaptations. Okay, I think I will have time, so I'll come back to this. I just want to make sure I don't rush through some of the applications. Okay. So the next thing is, if you do computation, you may maybe share the same experience as we have in our group, and I know that many other groups have. Particularly if you do like heavy computations, right? I mean, we do our simulations, we run our simulations in flux and in conflux, hundreds of cores in parallel. So people will say, oh, wow, that takes a long time. Yeah, sure. I mean, running the simulation takes a long time. It might take 2 days, 5 days, 4 days, whatever. But if you ask yourself the question of, in the entire modeling effort, in the time that goes from someone gives you the data to you have this nice PowerPoint presentation, if you look at how much time you're burning in the different tasks, for us, hands down, there's no even a contender, is parameterization. Okay, so we partly because of our approach to modeling, but I mean, that's what we have to deal with. We don't have enough data in the clinic. So it's parameterization. That means that you have to iteratively refine your simulations, both the mesh and also the value of the parameters of your model. It can be elasticity values of the vessels. It can be your heart model parameters. It can be your distal circulation parameters until you match the clinical data. Each of these iterations implies basically running a full problem, right? Which is, of course, expensive. But the expensive part is the fact that you have to do it over and over again. And what's frustrating about it is that it's, for the most part, a very ad hoc, non-systematic task. So because we have this kind of dream that this will be used available sometime in a clinical setting, we want this to be done without human intervention. Okay? And this is what I'm about to tell you now. So you already saw this. So we take a dynamical systems approach and particularly a Kalman filter approach. So what is the Kalman filter? So if you have a dynamic operator in a problem that you're solving, say physics, for us is first order ordinary differential equation. You can think of that. Navier-Stokes is this, right? You have a problem evolution in time, and in this case, you can even lump not just the model itself, but the parameters into an operator like this. Okay, so we have something that tells us how the system changes dynamically. So in the Kalman filter, we rely on observations, right? We're on the filtering theory. We rely on observations, and the observations can be basically whatever measurement you have. You need to be able to make a numerical counterpart of that measurement. So here I have a particularly tricky one. I mean, the obvious one would be, here's a pressure waveform. What is your computed pressure waveform? Do they match? In this case, it's a little bit more complicated. So the animation that you see here, the gray part that is kind of hard to see is the actual time resolved segmentations of the aorta from dynamic CT. So we know how the aorta moves. And then we also calculated in our fluid structure interaction simulation the motion of the aorta. And these two things are not going to match. And what we are doing here is we're comparing the position of the wall boundaries in the entire model. If our model over predicts the position of the data, it's painted in red. And if it's the reverse, it's blue. So in this case, we have this discrepancy field that affects the entire surface of the model. And this is mathematically expressed here. Z is going to be your data. In this case, the data is going to be the time series of positions of the wall. And h of x is going to be what you need to calculate once you have your solution to produce the numerical counterpart of your data. So in this case, it's our wall boundary calculations. And the difference between the two is a discrepancy. Yeah? And you want this to be minimum. If you think about the issue of parameter estimation, so you have the classical approach that relies on just a minimization, yeah? Least square. So you have this discrepancy between data and what your model produces. You put it square, you create your cost function like that, and you want to minimize it. You want those discrepancies to be minimum. And in doing so, you will obtain the parameters of your model that give you that minimum. This is great, but not super great for when you have dynamic data like we have, because you will have to somehow state this problem for the entire time domain of your problem. The sequential approach takes a completely different approach, which is explained here. If you go back to that first order operator, that basically the physics of your model, you say how X, your unknown, changes over time. What you do is you add a penalty term to it, which is the product of a gain, which you're going to have to calibrate, and then the discrepancy between your data and what your model produces. So this is, of course, you are no longer having a physically consistent model. You're adding a penalty term to it. But if you think about it, most of our models are wrong. I mean, we know are wrong. So a fundamental way to look at this is to have a balance of or a competition between how much you trust your model and how much you trust your data through the value of the gain. But from a conceptual perspective, if you are successful in reducing the discrepancies between your data and what your model produces by finding the right parameters, eventually this term is going to be zero. And you will be recovering the variationally, we use variational methods, the variationally consistent physical model. So when you are in the right set of parameters, you recover the true physics. And that's basically the way to look at this.
How much variability is there from person to person? So right now it sounds like you have one data set that you're comparing to.
No, we do, there's a huge variability.
The way it's looking here, we have this, our model over predicts. Is there variability built into that?
Huge variability, yes. Yes. I don't know if you're asking about uncertainty quantification, or just to the fact that.
A couple of things. How much variability is there from person to person? And when you say over predicts, are there tolerances in that?
Yeah, well, so first of all, there's a huge variability from person to person. And we do patient-specific analysis. So I've shown a couple of specific examples, but I'll show one more at the end of the class, and you'll see that. And then the tolerances, I mean, that's a more difficult question to assess, right? Because you have your numerical tolerances that you control. You say, I want to have an error that is less than this. But something that you do not control is the quality of your data tolerance. So your MRI is going to have a certain spatial resolution, a certain temporal resolution. You're going to have errors because it's not real time. So, breathing artifacts are going to affect. I mean, there are lots of people that are looking at this kind of problem, trying to put bounds to errors. And it obviously it's not a straightforward answer. So let me just, but this is not a stroll in the park at all. So, and there's various methods. I'm not going to get into detail, but so we have a specific family called the reduced order uncentered Kalman filter that does these estimations for you. What it does is, if you have a problem with p parameters, the method is going to run p+1 full-fledged simulations. And the reason it's doing that is it's basically sampling the solution space. Some of those simulations are way off, but you basically want to know your topology, right? And by doing that, you come up with a statistical description of the parameters, how they behave, and you end up obtaining an optimum value. So the value of doing this is that you don't have a smart PhD student or a postdoc doing these operations. Again, computing time is never the bottleneck, right? I mean, eventually we will be able to have what is now a $1 million system into a $10,000 system, and it will be able to do these things very quickly. So that's kind of the reason we're doing this. So let me show you. Let me show you a specific example. I'm going to show you the actual patient-specific. This is a synthetic data case. So this is, again, a completely different subject. This is one of my PhD students, and this is his aorta. And we took, in all of these blue circles, we took a whole bunch of phase contrast. That's a specific MRI sequence, phase contrast MRI, which gives you flow versus time. Okay, so we know all of these waveforms. We know the anatomy. We have 9 branches here. If we take our standard, 3-element Wien-Kessel model, we're going to have 27 parameters that we need to estimate, so that when we impose, for example, at the inlet phase, we impose the actual phase contrast measurement, we get something that looks like the data to the different branches. Yeah. So this is basically the way we go about it. We're going to have 9 compliances, 9 distal resistances, and 9 proximal resistances. We don't know what the solution is. So, and this is a problem that goes on in time, right? So this is roughly 6 seconds. Remember, this entail running 28 simulations. So it is costly. But again, no one touched it. I mean, the student clicked run and then came back on Monday. And here you see the evolution, right, for the 9 different parameters of each kind. And you can see how, there's some wiggly, but you basically reach a solution, even though every new second you have a full pulsatile simulation that starts again. You see that the parameters are fixed to a value, okay, because that's the physical meaning of them. We're looking at things, for example, it could be elasticity. Elasticity is not time varying, yeah. So they need to have a value. So this is kind of good news. We have identified a solution. I hope you understand that this is costly because it's, first of all, running as one simulation for 6 seconds of physical time takes a long time. But here we're running 28. But the system was able to find all the parameters by itself. Okay, how does this compare to the actual data? So when we run the final simulation with the optimally determined parameters, here is how our optimally determined simulation with the red curve compares in all these 7 different locations where we know the flow waveforms to the measurement. You see, that's a pretty good job. There are some cases where maybe your data has higher frequency components and the matching is not as good, but that's because your 3-element Wien-Kessel model can only reproduce so many high frequency components because it's a simple model. Okay, so let me tell you about something that for us is very exciting, which is we've done it already twice, which is, what you think of, the physicians have a complex case, they're not sure how to do it, and they give you 4 weeks. Typically, that's how much time they give us. These are congenital patients, but kind of adult. They're like between 15 and 20. So we have time to do it, but still very laborious. So just a little bit of background so that you understand the basis. So we're looking with patients that have congenital heart disease. That means their heart is not normal at birth. So this is the way a normal heart looks like. So you have the 4 chambers, the 2 ventricles. One ventricle, the right ventricle, is responsible to pumping blood to the lungs. The left ventricle is responsible to pumping blood to the rest of the body. Okay, and it's kind of like a double loop system. These babies, unfortunately, are born with an underdeveloped ventricle, either the right or the leg or the left, and that means that they're missing one pump out of the 2. So this is an example of having a hypoplastic. It means underdeveloped left ventricle. So obviously, if you don't have a left ventricle, you can't even live for an hour after birth. So they need to take care of this immediately. And they do it in a stage way. Here you're looking at the final result after 2 or 3 operations. And what they do is plumbing, basically. So what they do is the aorta, which is the main vessel that takes blood to the body, is hooked up to the one ventricle that works. And then obviously what happens is that you don't have a ventricle to handle the pulmonary circulation. So this is done by connecting the veins that bring blood back to the heart. Instead of going to the heart, now they are hooked up directly to the pulmonary artery. Okay, so the pulmonary circulation, blood gets to the lungs without ever touching the heart. Okay, this is kind of these T junctions that you see here. This is the best you can do because you only have one pumping chamber. Yeah. So this particular girl, I don't think I have the demographics, but she is 21, and this is the history of open chest surgeries that she had to endure. Okay, so she had this operation when she was 2, where these vessels were connected to the pulmonary artery. When she was 7, they kind of completed the circle, so the inferior vein was connected to the pulmonary artery. Then they saw that the problem I will describe in the next slide appeared, and they say, oh, well, let's see if it goes away. It didn't. So 3 years ago, now she's 21, came back, and they opened the chest again to redo the operation, and that didn't help either. And they just ran out of open surgery tries because it's super morbid. So they tried something else, and that's the reason they called us. So what happens in this patient, just the simplest way I can explain it to you, is the blood that comes from the lower part of the body which is going to be funneled by this vessel here, you need to make sure that it reaches both lungs evenly. The reason being is this blood comes back from the liver, and the liver makes lots of compounds that break down lots of things. And also, it is now known that among the things that the liver makes is a series of factors that prevent proliferation of new vessels. Okay, so you need to make sure that that's what happens in cancer, basically. When you have a very fast growing tumor, is because there's a lot of angiogenesis around the tumor. So the liver makes factors that make sure that systemically in your body you don't grow vessels for no reason. So if what happens is, if you shunt preferentially just because the way you hook up vessels, if you do it in a way that most of this flow goes to one lung and not to the other, there is a very strong evidence that the lung that doesn't receive enough flow from the liver is going to start developing these new vessels. Okay, and this is the problem. So these vessels basically are unintended junctions between arteries and veins. These are known in the field as pulmonary arterial venous malformations. So when that thing happens, so normally, this is, let's say that this is the artery. The artery should deliver, in this case, is deoxygenated blood to the alveoli, dump off the CO2, pick up the oxygen, and then come back through the vein. When you have these new vessels that form because that lung is not receiving enough factors from the liver, you're going to have these bypasses, basically. Okay, you have these grow, blood never makes it to the alveoli. You also have a short circuit of low resistance because you have arteries and veins connected together, which they are not supposed to. So this patient presented with a very low oxygen saturation. We all have between 95 and 100. So she had 70, really low. And she had a very high cardiac output at rest, even though she wasn't doing anything, but she had this short circuit. So you have the high pressure artery directly connected to the low pressure vein. So obviously you're going to have a lot of flow going that way because of the path of low resistance. So this is, in a nutshell, her problem. How often does this happen? A lot. So this is what this graph here tells you. This graph looks at in groups of patients that have maybe some abnormality in the venous circulation. Okay, maybe we all have differences inside, going back to your question, we're as different inside as we are in the outside. So these are patients that have maybe an interrupted inferior vena cava, but a normal heart. So they look at it, they look at these guys over time, and they say, do these guys have these problems in the lungs? And you see, after 20 years, nearly, after the operation, nearly all of them don't have these problems. Now, in patients that have abnormal venous circulation, like this girl did, and this kind of connections between the pulmonary arteries and the two veins, if you look at after 12 years, nearly 40% of them have this problem. And if you think about it now, if you don't think about optimally designing these, of course, it's going to be a coin cost. I mean, when you have the open chest there and you try to connect the vessels together, obviously you are thinking about the short term. The patient needs to leave the operating table alive. You want to successfully connect the anastomosis, which is the junction of the different vessels, so that there is no leakage. You worry about those things, but you don't really worry if you're a surgeon about. If I think about the perfusion of this particular vessel, oops. If I think about the perfusion of this particular vessel to each lung, am I achieving that in an even way? You're not doing that, obviously. So I think I've motivated the problem. So okay, I think this is. Yeah, there you go. So, and the literature also has plenty of evidence that if you manage to successfully, by redoing the operation, to successfully reroute and expose the lung that has these anastomosis to hepatic flow, they will revert. So the physicians know this, right? There are plenty of papers that show this. So, okay, so this is kind of the type of person that we're dealing with. So in this case, we had the CT scan of the chest. To make it even worse, these wires that you see here are a pacemaker. So that means no MRI, unfortunately. So we had to rely on ultrasound for flows, but we had lots of flows everywhere. We have lots of pressure everywhere, and this is the anatomy. So let me just play this. Yeah. So this is what we load in the software. We do the segmentation, and okay. So in this case, we have, like I said, flows everywhere, unfortunately, and this is the situation we're dealing with. So we have three vessels coming together. The names are not important. We have this one that brings almost 70% of the flow. This is the superior vena cava, about a quarter. And this is a small one, but the critical one, because this is the one that comes back from the liver. Okay, and we have two outflows. This is the right pulmonary artery and the left pulmonary artery. And you can see that these carries double the flow than this guy. So this is the one that has the shunts further down because it results in low resistance, right? And so total cardiac output for everyone in this room is about 5 liters per minute. This lady is 10 liters per minute at rest because of that low resistance. So to answer your question, we do specific analysis to each patient that we did. So we also have perfusion data. I'll get back to this in a second. These patients, unfortunately, they get so much assessment that is good for modelers. So we have a situation very clearly in which we have this vessel, these dots, let's call them, these are what the liver makes, that we worry about whether they reach both lungs evenly or not. So we know that in this case, it's going to be conceptually something like this. It's going to be mostly biased to the left lung of the patient, to your right. And then because another open repair was not an option, they said, what if we go with an endograft, which is something that you can deploy with a catheter? What if we deploy a stent graft in there so that we change how these three different vessels mix their flows, and we perhaps manage to get a more even distribution of the perfusion coming from this guy to both lungs? That was the question. And these guys recognize that it's such an engineering question that unless you do it somehow, there's no way you can guess, right? So we appreciated that very much. So the modeling process for this particular case, first from the CT data, we create the three-dimensional geometry of the vessels of interest. This is the one we really care about. This is the one where we're going to study the perfusion. And the first thing we do, just like I showed you at the very beginning of the presentation, is to parameterize our model until we match the data. Okay, so there's absolutely no prediction here. Okay, this is the result of a tuned model for this patient. So here we have the pressure, here we have velocity. So you can see that it's very high velocity here. Again, this is not a prediction. We know that this lung carries double the flow than the other. So now it's parameterized so that we have that. So if you look at our computed right and left flows, we have 6.3 in this simulation. We're happy with it, going to the right, and 3.3 going to the left. So once we have this, we say, okay, we trust this virtual characterization of the problem of the patient. Let's study perfusion, indeed. So what you see here is basically three things: the anatomy of the patient, the previous solution, the previous velocity field that I just showed you. And now what we're going to do is something called particle tracking, which I'm sure you heard of it. So what we do is we release a bolus of hundreds of thousands of little particles, and we see where this velocity field takes them. And you can see that, because of the way these vessels come together, even though this is a vessel of low resistance, most of the particles actually end up here. And we can calculate it, of course. Specifically, every particle, we can keep track of it. So, so what was the idea? How to do this? What was the actual operation, or in this case, endovascular operation? Based on the size of the patient, the stent graft was sized to be 13 millimeters in diameter and 50 millimeters in length. And what we consider was multiple protrusion lengths. So these we're looking at it from the left side. So this is the stent graft. And so we're going to consider a situation in which the stent graft is protruding 17 millimeters into the mixing zone. Obviously, it needs to be landed into the vessel for structural attachment. Then 20, 22, 25, 30, 27, and 30. So we run all of these preoperative cases, okay? Each of them is an individual analysis, okay? So, and we didn't know, maybe you run it and you get awful behavior for all. Maybe there is no optimum. Maybe there is no minimum for this particular case. In this case, there was. So here we are just color coding, in this case with path lines. Where do they go when we see them in that vessel? So the ones that go to the left lung of the patient to your right are red, and the ones that go to the right to your left is blue. So this is the pre-intervention. We already know is very biased. And those are the 6 different cases that we run. And we were very happy to see that there was an optimum. And that optimum is these 22 millimeter. Okay. So here is such case. It's hard to see, but now here you have a stent graft that is sticking in 22 millimeters, and you can visually perhaps already appreciate the difference. Okay. It's a little misleading because remember that the velocities here are much higher. So whatever particles go that way, they just get washed away very quickly. So, but the thing is, we can quantify things. That's why we are engineers. And this is kind of the uptake curve. So we look at percentage of the total bolus that makes it to, or percentage increase in this case, that makes it to the right lung, which is the one that needs it. So we see that there is an optimum and that 22 millimeter length. This is the specific table that tells us about the splits. So that was a good message that we said, we're happy there's an optimum. We told them these 4 days before the procedure, basically. We were really running against the clock. So we were happy that there was such an optimum. It's still not 50-50. It's the best you can do, though. It's, pretty close. But the thing that kind of shocked us the most, in retrospect, no, of course, but at the time when we did this is, what happens if you just push it, instead of 22 millimeters, you push it 1 centimeter more, you end up with a distribution that is just as bad as if you didn't do anything, right? Just think about how often these must happen in real practice, right? Where, yeah, the difference between an angle, maybe 1 centimeter is a bit extreme, but I don't think so, actually. It's pretty big distance when these vessels, they're not that big vessels, right? So it's of course, our indications to the cardiologists were very simple. This is all infinite precision in your in silico model, but we were very simple. Try to aim for roughly 20, 22. Don't go past that because we predict that it's gonna do poorly. So they did the procedure 4 days later, and you're looking here at an image of the after procedure. So this wire that you see here is the stent graft. These guys are incredibly skilled with their hands. So this is the sternum of the patient. Whenever you see these kind of rings, it means that they are metal rings that try to keep the sternum tight after it was opened many times. So this is the anterior aspect. This is the posterior aspect. They measure the length. So they nailed the 22 millimeters in the posterior aspect. The anterior aspect, of course, is not going to be circumferentially symmetric. It's less, following our recommendations. Okay. So, but right now, I haven't proven anything. I mean, this is all virtual so far, but because we could do it before the procedure, we told them about a couple of things they could do to verify if indeed what we were predicting was happening or not. And this is the neat thing about this. So we told them that when they were doing the procedure, they should do a couple of angiograms. So an angiogram is they have a catheter and they inject dye in the catheter and they see where it goes in the circulation. So we asked them to do it before and after. Okay, when the patient was on the table. So this is the preoperative angio. So this is the catheter. They release the dye on this vessel that we're trying to investigate, and you see a massive bias to the left lung of the patient to your right. Right, you almost see any contrast here. In our software efforts, we always try to draw things as close to what they are used to see, but this is basically a visualization of particle residence time. Okay, so whatever you see, lots of particles, the contrast is gonna look more intense. And we already knew, based on the simulation that I showed you, that was the case. So they inserted the device and then they did that additional angio. So you can see how the device is already in place now. And they release the dye and you see that bias is gone. So a much more even split of where that dye goes between the left and the right. And this was obviously also what our simulation had predicted. So for us, this was incredibly exciting. Both the cardiac surgeons and the cardiologists are, like I said, we have already done another case, and every time that they have a complicated case, we're gonna help them this way. The patient, by the way, did better. So 3 weeks later, the oxygen saturation went up from 70% to 85%. So it's an indication that we didn't really do anything therapeutic. What we did is to as best as we could, forward those anti-angiogenesis or angiogenesis inhibitors to that lung, and then hopefully they do their work. So yeah, I knew I would run out of time, so I wanted to go to the case. So thank you, and if you have any questions, I'll be very happy to answer them.
Same procedure routinely in surgery, where instead of doing the computations, just do the angiogram during surgery.
Yes, and what if they find out, as it obviously happens, that they did it wrong? Yes, they can do that, right?
But can't they adjust it as they're going, or is that not practical?
No, because this involves sutures, right? It's like you have to bring a vessel and connect it to a specific location. So undoing that is a major deal. So these patients
So
are.
you can't do the angiogram before you do the surgery.
You can do the preoperative angiogram. Yes, they do that all the time.
But not during surgery.
No, you need to finish the surgery and then do the angiogram, because you're trying to explore how it behaves, right? So yeah, and it happens, according to those papers, almost 40% of the cases, which is actually pretty good. I mean, obviously, the surgeon knows that I should get something even. It's not like a monkey is doing it, right? But there's still a lot of lack of insight for the specific flows and how the vessels come together that you can gain.
Thank you.
Thank you again for the invitation.